is epsilon oxide divided by the thickness of the TOX. So this will, you just plug in all the numbers here, and from the constants table, we should provide you the epsilon 0 and epsilon oxide. If you do that, then you will get the value. So I don't have the number here. Let me. I should have that. Okay, so I'll just show this for now. So you plug in the numbers and be careful about the units. So here, like 8 nanometer, you need to convert to the centimeter. That will be 8 times 10 to the power negative 7. So if you do that, you will get this 4.3 times 10 to the power minus 7. That is the COX, capacitance. And the second question is if the second one we still have the Km prime. Okay. So what is Km prime? Km prime is defined as mu n times COX. Since you have already obtained the COX, you just need to multiply by the mobility mu n, which is given here, 450. So you get 450 times this number, what you have obtained here. So then if you do this, you will get this 194 times 10 to minus 6. And then the unit for the Km prime is ampere per volt square. And this 10 to minus 6 will be micro. So it's microamp, 194 microamp per volt square. So that is the Km prime. So the second question here is to find the MOSFET voltage, like the VOV and VGS, to get the current, like saturation current, 100 micron. If the W over L is like 8 micron divided by 0.8 micron. So you just apply this saturation current equation here. This one. Drain current is half Km prime W over L, and then this VGS minus VT squared, which is this equation. And the VGS minus VT is defined as VOV. So that's why you have the VOV squared. So if you want to get 100 micron here, and then you have this Km prime, which is 194 micron. And then W over L is 8 divided by 0.8. That is given by the question here. So the only unknown is the VOV square. So then through this equation, right, you can solve for the VOV square. And if you do that, you will get the VOV 0.32 volts. 0.32 volts. So VOV is 0.3 volts. Now what is the VGS? So you know the VOV is defined as VGS minus VT equals to VOV. And the VT in this case is 0.7 volts. So you should have this 0.7 volt plus this 0.32 volts. That is your VGS. That will give you like 1.2 volts. That is the VGS you need to apply to get this 100 micron from this transistor. So any questions? So this is just plug in the numbers to that equation. Just be careful about the units when you convert the units. So here the rule is that to change everything to the centimeter. So then you'll be consistent. So the third question is find the values for the VOV if we want to operate this device as a 1000 ohm resistor for very small VDS. So what does this mean? We want to operate this transistor as a resistor with the resistance like 1000 ohm. That means we want to operate the transistor in that linear region. We want to use that approximation. So, you know the linear region? Here we have this resistance if we want to approximate the transistor as this resistance. Now the question is, this resistance is 1000 ohm. We want to find what is the VOV to make this 1000 ohm. So you have all the parameters ready, like 1000 ohm, and you know what is mu n COX, you know what is W over L, so you just solve for the VOV. So that is the approach. So I will skip that. And that is the approach you get the VOV. So once you get the VOV, you will get VGS, because VGS minus VT is VOV. That means VGS is VOV plus VT plus the threshold voltage. So here, this example is just to practice the equations. Any questions? So then let's move on to the channel length modulation. This is to consider the second order effect in the saturation region. We talked about earlier, we have this pinch off. So the pinch off point, okay, this is when we have the VD set. But if you further increase the VDS larger than this VD set, which is VOV, which is VGS minus VT. So if you further increase the drain voltage, so what will happen here is the pinch off point will shift to the left. Because you have larger drain voltage, you will extract the electrons from the channel even faster. So then the pinch off point will shift to the left. So if the pinch off point shifts to the left, that means effectively the channel length L will be reduced by this delta L. So your channel length gets smaller. If your channel length gets smaller, can you imagine the current will get larger or smaller? Here, this L is in the denominator. If L becomes smaller, then you can think the current will become larger. So effectively, we can assume the current will further increase with the drain voltage with the coefficient lambda. So this is because as the VDS becomes larger, then the channel length L will become smaller, so the drain current will become larger. That means drain current will increase with the drain voltage. So we give the coefficient lambda here. And that can capture this kind of a real IDVG curve, IDVD curve. So after you reach the saturation region here, this is the turning point we used to have. And we used to have a flat curve. But in reality, as we see in one of the examples from the last section, when we measure the current on the real devices, we will see the increase of the current even in the saturation region. So this is due to this channel length modulation effect. And if we modify the equation like this at this term, then we can capture the curve here. So the current will further increase with the drain voltage. So here we have a group of curves that depends on different VGS. But if you trace back all the curve, if you do a straight line here, if you trace back to this point, they will merge to this value. It's a negative voltage, and we call it early voltage, and that is 1 over lambda. Because we assume all of them proportion to the VDS, and the coefficient is lambda. If you trace them back, they will converge at this point, and this is called early voltage, and this is 1 over lambda. So this is the second order effect. So the first order, we think the current will become saturated when we enter the saturation region, but actually the current will still increase with the drain voltage. So we will modify the equation here to consider this effect. And but I think in our class here, in this class, we will not consider this. If I don't say we need to consider the channel length modulation effect, then you don't need to consider this. This is second order effect. This is because for the digital circuits, we do not care about this too much for digital circuits. But if you are designing the analog circuits, then this is very important. This effect is very important for analog circuits. But we are talking about the computers here. For the digital system, then this effect can be ignored. Okay, so this is the channel length modulation, and we will stop the lecture